Let's look at 3.2. We're going to look at measures of dispersion. We also call these measures of variation or measures of spread. So let's look at an example to start off with. So to order food at McDonald's, one must choose from multiple lines, while at Wendy's, one orders a single line. So there's still McDonald's that have single lines, but just for the example, we're going to look at multiple lines. So we have some data that represent the wait time in minutes for a simple random sample of 30 customers. So there's our data. So for each sample, we want to look at the mean wait time, draw a histogram, and then look at which restaurant wait time appears to be more dispersed. So by dispersed here we mean more spread out, and which line will we prefer to wait in and why. So there's our histograms there. So the mean wait time at each line is 1.39 minutes. So they actually have the same mean. Right? So looking at the histograms, we see that McDonald's seems to be more spread out, right? So Wendy's just kind of runs, is bunched up right here, right? McDonald's is spread out, right? So, since they have the same mean, but they're spread out, we need a measure to describe that. So that's what we're going to focus on in 3.2. So, first and easiest measure of dispersion is range. We use R to represent that. Is the difference between the largest data value and the smallest data value. So, again, we're going to go through some examples. I'm just going to go through these. Another measure is called standard deviation. So again, we have one for population and one for sample. But this time they're computed slightly different, and again the technology will compute these for you. There's different symbols that represent these. So what it is the square root of the sum of the squared deviations about the population mean divided by the number of observations in the population. So that's the square root of the mean of the squared deviations about the population mean. So we use the lowercase letter Greek letter sigma here to represent population standard deviation. So you can see the formula there, it's quite involved. So each of these things here, we're just taking the data value and subtracting the mean. Those are what we call deviations. A deviation is just how far a data value is away from the mean. So it may be positive or negative. So if the data value is smaller than the mean, it's going to be negative. If the data value is greater than the mean, the deviation is going to be positive. And then we square those and add them together, divide by how many observations we have, and then take the square root. And here's the computational formula. It's a little bit easier. Again, you don't have to do it by hand, but if you would like to, that's your option there. So you can kind of see the process here. And then using the computational formula. So you can see they're a little bit different. So sample standard deviation, we represent that by the letter S. And instead of dividing by n, we divide by n minus 1. So you can see same formula there. We're just dividing by n minus 1. Computational looks the same, except for this is n minus 1. And we call the n minus 1 degrees of freedom. So basically what we're saying, so if we have 5 items and we can pick them in a certain order, that last item we don't have a choice. We have to pick that. And we're going to look at degrees of freedom later on, so just kind of keep that terminology in your mind. And the reason why is the sum of the deviations about the mean always has to equal 0, so that value is kind of forced upon it. So again, you can see an example there using the formulas. So we go back and compare the two standard deviations for McDonald's and Wendy's. The sample standard deviation for Wendy's is 0.738 minutes, and the sample standard deviation for McDonald's is 1.265. So to kind of look at the range, we saw that McDonald's was larger than Wendy's, so we have an anticipation the standard deviation would be larger, and that's because there's more dispersion. So the larger the range, the larger, or the more dispersed the data is. The larger the standard deviation, the more dispersed the data is. That just simply means our data is more spread out. The data values are further away from the mean. So variance of a variable is just the square of the standard deviation. So whatever your standard deviation is, you're just going to square that value, and that's what we call variance. So again, there's the symbols for those. So again, example, we're going to go in detail on that in a minute, and then we'll talk about empirical later on in detail as well. But you want to commit those values to memory. So 68, 95, 99.7. And then if you can figure out how to obtain those values here on the 0.15, 2.35, 13.5, and 34, then you don't need to memorize those. If you're having a little bit of difficulty with that, you want to do that. And I'll have video that shows you how to go through that as well. So we'll go through an example of empirical rule. So if you didn't notice here, this says if a distribution is roughly bell-shaped, so that we can only use that if it's bell-shaped. So we're going to look at Chebyshev's inequality, and it says for any data set or distribution. So we can use this for any data set, whereas empirical rule is only used for bell-shaped data. So this says at least a certain percentage of observations lie within K-standard deviations. And we'll do examples of these, and I'll go in more detail with those. Just wanted to overview what was in 3.2. So I think that sums up 3.2.